Hello, everybody. This is Aiden from InPlay. Today, I'm going to be talking about the I100 I2C configuration options. However, most of this video is going to focus on some power-saving techniques you can use to help you make a more power-efficient setup with the IN100 and your I2C sensor of choice. So, just to start off, I'm going to briefly cover some of the I2C configuration options here. We do have plenty of resources online that also cover this information. So if you're interested in having some more in-depth stuff, you could go ahead and reference some of our older videos or our GitHub, which also has a section on the I2C on the main page. Okay, to start, when you open the config tool, you'll be open to this advertising page here. To access the I2C, you simply click on this tab on the left, and you see our three I2C slave options here. So we have I2C slave 1 through 3, right? So this could allow you to use three different sensors connected to three different I2C slaves. So I'm just going to go ahead and enable one and hop into the settings here. So you have the option of selecting a clock line and a data line. And just by the way, if you are confused about I2C stuff and you want some sort of like information on how I2C works and how the whole protocol is meant to be performed, there's plenty of options online. So for example, I found this article by circuitbasics.com, which covers the basics of I2C protocol and how it's meant to work. Basically, you have a master, which has a data line, and a slave that also has a data line connected together, and then a clock line, right? And then one will pulse out the clock and then the data it's sending, and then vice versa to allow this sort of two-way communication. So it's a very common protocol, plenty of resources online. All I did was search in I2C protocol on Google, and you'll find articles like this. Sorry, back to the config tool here. So you can choose a clock line or a data line. And all you have to do when you're selecting these lines is make sure that the GPIO you're selecting is not being used for something else. So for example, GPIO 0 and GPIO 1 for the 18-pin IN100, which is the same one on the development kit board, are used for the UART. So this option here for GPIO 0 would conflict with the UART settings. You are able to overwrite the UART if needed, but most of the time I would simply recommend just to stick to something that's not used already, just to make it less complicated. Okay. For addressing mode, we have 7-bit and 10-bit, both standard addressing modes. So you can go ahead and pick one depending on what your sensor needs. And then we support 100 kilobits per second, standard I2C speed. And then we also support fast mode, which is 400 kilobits per second. So, if you want to save a little bit more time, make those I2C transactions faster, we do have this fast mode to support that, depending on if the sensor also supports it, right? And we have the slave address, which you simply enter the value in hex. So for example, let's say it's 4E, for example. It could be, any hexadecimal address, right? All you have to do is make sure it matches what's on the data sheet. Switch zero power control, I will get to in a minute. Okay, read data storage settings. So these two options are grayed out because they're simply set in the I100's registers address, right? So the I2C stored data, what's read from your sensor when you're reading from it, is stored starting at this memory address in hex. It's 2300. So it's simply locked like that. And then I2C number 2 would be here, but offset by 16 bytes, right? And then I2C number 3, sorry, would be another 16 bytes offset from this. So it's this 3 blocks of 16 bytes reserved in the memory for I2C purposes. Now there's this option for the length of read data storage settings. So basically, you're going to be telling the I100 how many bytes you want to be reading from the I2C at most, right? So by default, this is 2. Most of the time, you'll have something like, it'll be like 3 bytes of temperature data, 3 bytes of pressure data, 3 bytes of accelerometer data, then followed by a CRC. So you'll see very common options will be something like 4, or it'll be 2 bytes in a CRC, so you get 3, for example. But you just follow your data sheet, right? Whatever that value is. Okay. I2C commands here. This page is can be a little confusing if you're not familiar, so I'm just going to cover some of these options here. I2C read is, of course, if you want the master to send a read request to the slave, you go ahead and enter the length here. So let's say I just want to read 3 bytes. Now you have the option to execute in cold boot, execute in warm boot, or both together, right? You have to have at least one so that it knows when to execute. Cold boot is basically when the I100 wakes up from a powered off state. So say, you put a battery in and it turns on for the first time. That would be a cold boot. Or you reset the system. That's a cold boot. And then a warm boot is just a wake up after being in the sleep state. So, it wakes up to advertise, for example, but it had advertised previously. It wasn't just, coming back to wake from a powered off state. That would be a warm boot, right? So you have the option to have both of these and then, just one or the other, whichever you needed, right? So for example, for cold boot, you might want to have some of the settings to configure the sensor, right? You might want to write to some addresses of the sensor and say, okay, I want it to operate like this. You probably only want to do that once, right? Because it takes time to configure the sensor every time. And so you'd only want to do that during the cold boot setup, right? While warm boot would be regular stuff, such as like, reading from a specific address in your I2C. Okay. So anyways, I2C read, you just enter the length you want to read and you click add, right? And then you get I2C read and then 3 bytes. That's what the 3 represents here. You see you get added in cold boot. Or sorry, the 3 represents being cold and warm boot, while a 0 represents being cold boot. And then a 1 or a 2 represents being just warm boot. Sorry, going back here. So you have the 3 read, and then you have this I2C null. This is basically sort of like sending a stop bit, right? You'd want to have this between, transitions between copies of the same command. So you might have a block of reads, and then you'd want to have an I2C null. And then you might have like a block of writes that you're doing, and then a null between those. Okay. Backing up, you have I2C write. You just enter the address of whatever register you're trying to read. So let's say it's just register 10 on some slave. You hit add here, and you can see it executes in warm boot by this 1, and then it reads or writes to address 10 in hex. Okay. I2C write stop read basically does a write, sends a stop bit, and then does a read. So it's just sort of a combination of these two together, just so that you can conveniently enter it in one line, right? So if you know you're going to do a write stop read, you can just have it done in one line here. Let's say I write to register 0x10 in hex, and then I read 3 bytes. And then I go ahead and click add. You can see I write, stop it, and then read 3. Okay. And then, of course, a delay command, you simply enter the value in microseconds here that you want to delay. So let's say we delay 1 millisecond. I would enter 1000, and I click add. And then you get this wait command. Okay. What else can we cover here? Of course, we have this also the insert option. So say if you have a setup of commands here, and you say, okay, hold on, I wanted to insert a write here. I click where I want to insert above, and I click insert, and I have that write command inserted above. And of course, I can delete individual commands. Say if I entered the wrong number here, I entered 4 instead of 3, I could just delete the last one, for example. Okay, so that's the basics of setting up the I2C commands. So what exactly the commands will be will, of course, follow, whatever sensor you're using. Okay, so advertising, when you're editing an advertising field, right, and you want to add your I2C data, that's an option in the manufacturer-specific data. You can see I2C slave number 1, 2, and 3 here. So let's say I'm just slave number 1. You can offset what you're reading. So say if you read 4 bytes, but you only want the last 2, you'd have an offset of 2, right? And then how many bytes you're reading. Of course, this value here at maximum is going to be 16. And you have to reflect that in your read data length, right? So it has to be 16 here if you want to read 16, right? This is the maximum that's going to be stored in the I100 from a read, right? Okay. Back to here. So I can say I want to read 4 bytes from my I2C slave number 1, right? And then, of course, there's an option to encrypt it if you're using encryption. And then when this advertises, you'll see, this first 4 bytes here would be I2C slave number 1 read results here. Okay. Backing up a second, another thing to know about the I2C interface is we have the global trigger settings. Of course, I cover this more in depth in other videos, but you could go into global trigger settings. Let me back up down here at the bottom of advertising section. And you can pick the I2C slave as the trigger source and say, hey, if the read result is below 10 or it's above 20, then I want to trigger my advertising set. So that would be how you would set trigger thresholds, trigger based off of I2C data, would be through this global trigger settings tab. And again, if you want more information on this, I did cover it more in the advertising set configuration YouTube video. Okay, now that's most of the configuration settings. I do want to move on to some of the resources we have online. So we have this GitHub that we have set up that's maintained by me and some of my colleagues, right? It's github.com/nanobeacon/config files, right? And this is the main page here. You can see we have a bunch of different resources for the IN100. We have a description of partner links, websites, and resources. I talk about IN100 support here, how to set up a config file, and I cover the basics of I2C configuration in more detail here, right? So sort of everything I said in the video, just a little bit more advanced. In some sections, I sort of go through how the I2C commands are set up and how you would, how to read them as well. And then we also have these different sort of sensors that we've worked with, right? So most of these are sensors that I've worked with personally. Some of them are sensors that our partners have worked with, but have been kind enough to share the config files with. So for example, we could go to this Bosch one, the BME 280. You see it's a pressure, temperature, and humidity sensor from the description up here. And I sort of go through these two examples here, or this example here, which is this force mode, which is based off of the data sheet of the BME 280, talking about its force mode settings. And I go through sort of the power profiling of what it looks like using this mode here. So this can sort of get you started with this sensor, for example, and any of the other options we have here. So I want to go into a little more depth about some of the power saving options you can use with the IN100 when using a sensor. So you might run into a situation where you have a sensor that has a long time where it needs to be awake. So say if you wake up, you want to write to one of these registers, and then the datasheet says you have to wait for 5 milliseconds, and then you can read the data. That's a long time for the IN100 to be awake. If you're not aware, the IN100 sleep current is very low, right? You'll get something like 650 nanoamperes on average. So to maximize to get that optimal power consumption, the IN100 should be asleep more often than it is awake. And so when you have these long sections of being awake for an I2C sensor, you'll suddenly increase your average current consumption by quite a lot. You can see based off of this config file here, using the Sensirion SHT4X series of sensors, I basically just follow this basic sort of sequence where I write to this register OXFD, which gets the temperature and relative humidity. Then I wait, and then I read the 6 bits that are responded with, right? That gets me the temperature and relative humidity bytes here. You can see it takes a long time to have all that done, right? That's a long time being awake. So to counteract that, I sort of cover these other options here. So there's this other option called the low power mode, which I've called. Basically, the strategy is instead of, writing to register OXFD and then waiting while we're awake and then reading, I will read the last result right to that same sensor register FD, and then have all that waiting time done while I'm asleep, right? So I'll write, I'll read, but the waiting time in between, those like 5 or 6 milliseconds that I have to wait, is done between sleep, right? And that allows the sensor to have all of its data processing waiting for the data to be ready when the IN100 isn't awake, right? And that allows the power to be a lot more efficient, right? Because when the IN100 is asleep, its current consumption is not nearly as high, right? So now the sensor data is being processed here, and then it's ready to read when I wake up. And so if you're a little bit confused about sort of that process I set up, you can go ahead onto our GitHub and look at the low power config file and read through this section here, and you'll sort of understand my approach here. Okay, you can see the power consumption results, 16.118 about microamperes, versus the regular approach, which got me 41 based off of how much longer the IN100 has to stay awake to process the data, right? Versus when it's asleep and the sensor's processing that data, a lot more efficient, right? So, nearly a fourth of the power consumption. Okay, then I want to talk about this other strategy, power switching, right? So if I go back here to the I2C section, we have this option for power switch control. So the IN100 18-pin package has access to 2 power switches, power switch 1 and power switch 0. Power switch 0, when it's on, will connect, its pin to power when the IN100 is awake, and then it will pull to ground when the IN100 is asleep. So this allows you to turn on and off an external sensor when you need it to be on, like when you want to read the data, and then turns it off when the i100 is asleep and does not need access to the sensor. So this is a very useful feature when the passive power consumption of a sensor is very large, right? So you might have a sensor that has a passive power consumption of a couple milliamps, right? That is quite a bit, and you wouldn't want that to be constant, especially if the i100 is going to be operating for a long time. It'll quickly eat away at your battery to basically increase the average current by 1 milliamp, and then on top of that, have the i100 wake up and advertise to increase the current consumption more. So this is an option for sensors that will have that stronger passive current consumption. You only want them on when the i100 is on, only when you need it, right? However, one of the drawbacks of this strategy is that you have to configure the sensor every time you wake up, because when you power switch it, when you turn it off, it will reset the sensor. So if there's any configuration settings you want to add in, you'll have to do that every time the i100 wakes up, which will extend the wake time of the i100 to configure that sensor when you turn it on and off again with that power switch. Now that may sound bad, but in some sensor setups, this is better, right? So if the passive current consumption of that sensor is large enough, this option will be good, even if it has to stay awake longer, because the average current will work out to be better. In the case of the SHT4X, it doesn't happen to. It's about the same as that regular strategy above, right? About 41 microamps versus our more efficient strategy around 16 microamps. And then this power switching option around 41 again, right? So it saves a little bit of power when asleep, but that longer wake time sort of averages out to match the original strategy, right? So in this case of the sensor, it's not really beneficial to take this approach. However, this is at a 1 second advertising interval. And the longer it takes the i100 to advertise, say 1 second is pretty quick. Let's say you're only advertising once every minute, once every hour. In that case, the passive power consumption is going to be way, way, way longer than this awake time, which means if your sensor is off, you're going to have a lot more time of lower power consumption when it's asleep, right? So I have this table to compare, which has the regular method I covered first, the low power option, which again is, you read and then write and then wait for it to sleep while the i100 is asleep, and then read when you wake up again. And then this power switch when you turn the external sensor on and off. You can see I have these different intervals, right? So you can see the regular method, the energy estimation in millijoules versus the interval, and then how long we could estimate that would survive for some specific battery, the CR 2032 coin cell, right? A common battery choice. You can see at 1 minute, this low power option is going to win out. But if I jump down to the longer advertising intervals, the low power option still performs better than the regular method. But now the power switching option is far better, right? When we're at this longer advertising intervals, having that sensor be off and lowering the average power consumption when the i100 is asleep affects the system a lot more when it spends more time asleep, right? So it's a much more efficient option. So, which of these approaches is going to be best is really going to depend on your sensor's data sheet, how it's set up, how long it needs to actually stay awake to, get all the sensor data out. And it's also going to depend on your application, how long you need the i100 to be advertising, right? If it's every second, you might want something like the low power mode or the regular mode. If it's going to be a really long time, you say the i100 advertises a couple times a day, then this power switching option is going to become a lot more efficient, right? So it's really going to depend on your use case. These are just a couple strategies for optimizing the power consumption. For any sort of sensor setup, right? This sort of works on any sensor, with the caveat that some sensors are going to work from some approaches better, and then different approaches are going to work on different i100 settings and setups, such as the interval, right? Okay, and then just as a quick aside to finish off the video, we also have the same option for power switching for the ADC, right? So if you have an ADC sensor, we also have the option for power switching. So if you're not using I2C and you're using an ADC sensor instead, analog to digital, we do also have this option to turn off with power switching. So that's an approach that also applies to the ADC sensor stuff. Though this video is mostly about the I2C, so I just wanted to briefly mention that the same strategy, the power switching, applies both to I2C and to ADC sensors, right? It's an option for both. But anyways, if you have more questions on I2C, of course, we have plenty of resources available on our GitHub here in our config files section, right? We have plenty of tutorials on i100 and other aspects besides I2C and sensors. So if you're interested in learning more, you can find the link to our GitHub on our website, or you can find it on Google just by searching up NanoBeacon GitHub. And you'll find plenty of resources, plenty of options. And of course, we have plenty of videos on our YouTube channel. And you can reach out to our support email if you have some more specific questions that you feel have not been answered. Anyways, thanks for joining me. If you have more questions, go ahead and reach out to us, and we'll be happy to help you out. Thank you.